Hello, and welcome back to Physics for the 21st Century. My name again is Greg Perugini, and today we're on the topic of energy. Now, energy, this is a fairly complex subject, so this is going to take us a little bit of time. Uh, the energy that we're going to be talking about uh, can be related in three different forms. We can talk about kinetic energy, which is associated with movement, potential energy, such as gravitational or elastic potential energy. We'll define each of these later. And internal energy. Now that's related to the temperature of a system. The top two, kinetic energy and potential energy, are mainly our concern in this chapter. Changing in the temperature in the system and thermodynamics, that is for another semester. We can have systems that are non-isolated, as in energy can transfer across the boundary, can enter into the system. And that changes the total energy in the system. But isolated systems, by that definition, the energy in the system is constant. When we talk about conservation of energy, we can say that no non-conservative force is acting on the system. Non-conservative forces are things like friction, work, and this applies to biological organisms, technical systems, engineering situations. So we can talk about, in an isolated system, that energy, in a non-isolated system, energy can cross the boundary by means of work, a mechanical wave, heat, matter transfer, electrical transmission, or electromagnetic radiation. But in an isolated system, energy is conserved. This means that energy cannot be created nor destroyed. It can change its form. It can go from potential energy, whether it be of gravity, potential energy due to a spring, or kinetic energy, the energy of movement. We're going to define all these in a little bit. The total energy of a system would not change. The potential energy as something falls will go down, and of course as it falls, its energy of movement will go up. But the total energy in the system will stay constant. Everything's going to stay constant in the total energy of the system. So, the energy forms that we're going to be using in this semester, let's look at it here. Kinetic energy. Well, that's 1/2 times the mass times velocity squared. Gravitational potential energy. Mass times gravity times the height. Potential energy, put that there, sorry. Potential energy due to spring. That's going to be 1/2 k, the spring constant, times x squared, the distance squared. Energy can be transferred between these systems. Energy can be taken from the system via work. So, work can be done by a change in kinetic energy. If I leave out the potential energies and say the only thing that is happening is I'm changing the kinetic energy, I speed something up. So my kinetic energy before does not equal the kinetic energy after. I've added work to the system. And it's a non-conservative force, and hence I have added energy to the system. The kinetic energy would go up. I can change the potential energy of something by just raising it. Say I lift it from 1 meter up to 2 meters up. The potential energy due to gravity, the final is greater than the initial here. And hence, there is energy that has been added to the system. That energy was done by work. And of course, there's the potential energy due to a spring as a spring relaxes and the compression goes out. It is no longer held in as potential energy. It becomes, as it moves something, say it's a shooting of a little BB gun or something like that, it's going to move that ball down the barrel. Hence you have a kinetic energy. Let's do a couple of examples. Let's take this example here where we're dropping a ball. So I have this printed out so we could just put it right up here so we can refer to it. So we're dropping this ball. And what do we know? Let's just write down a couple things we know here. We know that the ball is 2 kilograms. And this height off the ground, at a height of, let's just say 120 meters. Okay? So we're at that height. So the question is the velocity when it hits the ground. Now we can use our kinematics for that, but let's use energy to figure it out. Before we let go of the ball, is there any kinetic energy? No. There isn't any. Right? It's not moving, so there's no velocity. Is there any spring? Well, there's no spring in this. It's all potential energy due to gravity, which is mgy, which is equal to 2 times 9.8 times the height, which in this example is 120. That is 2352 joules. So it's important to note that at that point, the energy of this system, if we isolate this as a system, and we're not going to assume any frictional force like air friction, for instance, that this is going to be, every point along this line is going to be the energy before is equal to the energy after. Energy is conserved. So after, let's talk about the afters. When it hits the ground. When it hits that ground, what is the potential energy? Well, we're at a height of 0, so that's going to be 0. There's no spring again in this. So it's going to be all kinetic energy when it hits the ground. All 1/2 mv squared. So, the total energy in the system doesn't change whether at the top or bottom, is equal to 1/2 times the mass, 2, times velocity squared. You got one variable here. Solve for that variable. That leads us to 48.5 meters per second. Again, we could have used kinematics for this. Here's another interesting question we could ask ourselves. What happens if we're 75 meters up? Not at the ground. We're going to ask now the question, at 75 meters high. Well, do we have kinetic energy? Yes. It's 1/2 times the mass. We don't know the velocity. That's what we're trying to figure out. Do we have potential energy? Yes. It's, in this case, 2 times 9.8 times 75. Okay. But if I add those together, what do I have to equal? The energy of the system hasn't changed. At every point, it's going to be 2352. It has to equal 2352. So, you have 2 times 9.8 times 75 plus 1/2 times 2 times velocity squared equals, solving or leading to velocity squared equals what? Velocity squared 29.7 you should get, or I should say velocity is 29.7. If you take this plus this and equal it to that, you have only one variable and solving for that variable. Notice it's not going as fast as you would expect. We're 75 meters off the ground. It's speeding up as we go down. Okay. So we determined the speed of the ground at a height, at a given height, whether it be at 75 meters or at 0 meters. Let's take this BB gun example. Another similar type of example where we have to solve for the energy of a system. We're determining the maximum height this ball goes. So if we look at this, let's say this spring has a spring constant of 2,000 newtons per meter. Okay? Let's say this little BB, this little pellet here, is 2 grams. Let's say this compression, when we push back and compress the spring, we're compressing how much? Let's say 4 centimeters. So the question we could ask is, how high does it go? So let's look at the befores. We've cocked it. We're at this point of A. Okay, so we've brought it down to A. We haven't shot it yet. So what's the energy in the system? Is there any potential energy due to gravity? No. Is there any kinetic energy? Is it moving? No. It's all potential energy due to spring. And that equals 1/2 times k times x squared, which is equal to 1/2, in our example, 2,000, times the compression of 0.04 squared. Well, we'll do the calculation for this, and you can do that here. What do we get? 1.6 joules. That doesn't sound like much. But again, we don't have to shoot anything very big here. After, when it reaches the very top at point C, do we have any kinetic energy? Well, at the very top, its velocity is equal to 0, so no. Do we have any potential energy due to spring? No, the spring is totally out of the picture when the ball's up there. No. Do we have any potential energy due to gravity? Yes. That is mgy. That is equal to, in this case, mass of 0.002 kilograms, 9.8. We don't know the height, but we do know the energy before and after must equal. We know the energy after. So, or excuse me, before we shoot. So that has to, of course, equal the energy after. Equals this. So 1.6 joules is equal to 0.002 times 9.8 times y. Solve for y. Therefore, y is equal to, I'll let you solve, but the height, give you a second, so you can pause it here, but what do you think the height would be? Okay, 81.6 meters is what you should get. So that's another typical example that shows you conservation of energy. Let's take this one. Determining the speed at the bottom of a ramp. So this box is going down the ramp, and we're trying to figure out what the speed is going down this ramp. So, well, there's a few pieces of information we need to know for that, right? We need to know how much the box weighs, of course. Right? So we know that box, I should say its mass, is equal to, let's just say 50 kilograms. We see the height, this height here. I'll draw it a little better because that could be a little sketchy to see. This is 0.5. Let's say this is 30 degrees. This distance it's going is 1 meter. And it's starting off at 0. velocity initial equals 0. We want to know the velocity at bottom. Okay? The velocity here. Again, we can do this with ramp physics if we wanted to do that. But let's do it with the energy, using energy. The before. The box isn't moving. So do we have any kinetic energy? No. We could just leave spring out of this, right? There's no springs in this. So it is all potential energy due to gravity. mgy. We are at a height of 0.5. So our potential energy is the mass, 50, times 9.8, times the height, 0.5. And you do the calculation for that. And you should get 245 joules. After, we're at the bottom. Is there any potential energy? Well, it's all kinetic energy, right? It's all moving 1/2 mv squared. There's no potential energy due to gravity because we're at the bottom. Y equals 0 at the bottom. So we have the total energy still being 245 joules. And that is going to be equal to 1/2 mv squared. In this case, 1/2 50 times velocity squared. There's your equation. With this, we can solve for velocity. And what do we get for velocity in this case? About 3.13 meters per second. So at the bottom of this ramp, we're going a velocity final equal 3.313 meters per second. Now we could do a calculation to figure out the acceleration if we want to do that, right? Using that velocity, we could check our velocity number very easily. Because our velocity initial is equal to 0. And the distance we're covering is 1 meter. Well, I can use the kinematic equation, velocity final squared equal velocity initial squared plus 2a change of x. And I'm going to get 3.13 squared equals 0 squared plus 2a change of x. Well, we know the change of x, right? 1 meter. Distance of 1 meter. And you're going to get an acceleration of about 4.9 meters per second squared down the ramp. Now, if we used ramp physics, we know the acceleration due to gravity down this ramp is equal to g times sine of the angle. And of course, if we do that calculation, we are also going to get 4.9 meters per second squared. It's a little check on our work here. So with conservation of energy, we could check our ramp physics or vice versa. But with just conservation of energy, we see that the total energy of the system going down 245 joules is at the top, it is at the bottom, converting from potential energy due to gravity down to potential energy due to or down to kinetic energy. So, remember, kinetic or energy with potential energy with spring energy together, they're all conserved. They can be transferred between each other. But the befores must equal the afters. Unless there's something lost to friction or another non-conservative force, the befores must equal the afters. Now, I might have done some work in this previous example, moving this block up here, right? And I could calculate that in joules as well. If that work was added to before the system, i.e. I did that to get that block up there, I've added energy to the system, right? To move it from here up here, the system had no joules, and then I moved it up there. I added, in this case, 245 joules to the system. So be aware that work can be calculated as a change in potential energy or a change in kinetic energy between 2 points before and after. When I move something, lift it up, change its potential energy due to gravity, or when I accelerate something, changing its velocity. So there you have it, energy. And good luck.